4.3 Riemann sum. Alright, so for the definition, I would like you to read yourself in the book, but I will explain it from the example. Alright, so the first theorem I would like to talk about is Theorem 4.4. It said that if the function is continuous on a closed interval AB, then it's integrable on AB. So which mean that if it's continuous, you can take an integral, right? So this is the definition of Riemann sum, and which is equal to the integral of a function. Basically, the idea is if you have a curve or a graph and you want to find the area under the curve, you build a rectangle, alright, and the width of the rectangle is getting smaller and smaller, and you have n rectangle, then you can find the area under the curve. Alright, let's look at our first example. The first one, I have an integral from 1 to 4, 4x squared dx. For part A, I will take an integral by the definition of integral. Alright, I bring out the 4. I left with an integral from 1 to 4 x squared dx. Alright, x squared dx, if I take an integral of that, I will have x to the third over 3. My upper bound is 4, my lower bound is 1. I substitute my upper bound 4 here minus the lower bound, which is 1 here, and then I simplify it. I get 84. So the answer should be 84 if you use the definition of an integral. Now the second part here, I'm gonna use the limit definition, which is this one right here. So as the theorem said, it should be equal. So an integral a from a to b f of x dx should equal to limit as norm of delta go to 0, sigma I equal to 1, f of ci delta xi. So first thing, I'm going to calculate my delta x. My delta x, the formula is b minus a over n. B is 4 right here. This is your a and this is your b. The lower bound is a, your upper bound is b. So 4 minus 1. We have so many rectangles. In this case is n, which eventually we're going to take a limit as n go to infinity. So leave it as n. So 4 minus 1 is 3. 3 over n. Now my ci, think of it as x because you're going to have f of x. Think of it as x, a function. The formula is a plus I delta x. My a is 1. In this example, this is my a, which is 1. I is just I. Delta x, I just calculate here, which is 3 over n. So I have 1 plus 3 over n I. Now, because I want to calculate this, I have to take a limit, but I don't have space for it. I'm just going to calculate this part first, and then I take limit later. So sigma I from 1 to n, alright, f of ci delta xi. Sigma I from 1 to n f, my x is right here. My x is right here. 1 plus 3 over ni. This is my x. Delta x is right here. Look at the original function. I have 4x squared dx. So I'm going to have sum I from 1 to the n. My 4 is my 4 here. My x is my x here. But I have x squared. So I have to square it. The dx is delta x, which is 3 over n. If your equation, just to understand, if your equation is 4x to the cube, you're going to have 4 here, and your x is right here, your ci. You're going to have 1 plus 3i to the cube. And delta x is 3 over n. Delta x is dx. Let's see continue our example. Hi, so from here, I rewrite here again. What I did was I multiplied the 4 and the 3, I have 12, I pull out the n over here, and left, I expand 1 plus 3i over n squared. If you expand that, you're going to have 1 plus 6i over n plus 9i squared over n. The next step I did was, let me see, I used from here, I used the definition of sigma, alright, sigma, which is from the previous section. If you go back to previous section, I give you the definition of sigma when you have variable I from 1 to n, and I expand it. This is the result of apply the definition of sigma and expand it. So the sigma disappear, you end up with all this term. Next step I did, I distribute or multiply 12 over n inside. So the first term I just get 12, and I multiply 12 over n to the second term and the third term. So I end up with this. As you maybe remember, because we didn't have room, we only did this part, we didn't take a limit. So to get the integral from a to b f of x dx, I have to take limit. So from here, I take a limit as n go to infinity. So I apply limit as n go to infinity to each term. So to 12, to this term, and then to this term. That's how I get all this. Now limit of constant is just constant, which is 12. Because of this term, I distributed 36 in, so I have 36n plus 36, but all of this multiplied by n. Then I break it down into part and then simplify it. Same idea as this one. So limit as n go to infinity of 36 is just 36. For this one, as n go to infinity, you get 0, same as the rest. So you end up with 12 plus 36 plus 36, which is 84, which is the same thing that we use definition of integral. Okay, let's see the next example. Hi everyone, let's look at our next example. I have example here, evaluate an integral from 2 to 6 of a constant 8 dx. Another would think of it as f of x equal to 8 or y equal to 8. So instead of taking integral and use the definition of integral, I'm just going to draw you a picture and explain to you what it means. Alright, so we have y equal to 8. So my y is 8. Alright, and an integral from 2 to 6. So my x is from 2 to 6. So if you draw the picture, you can see this is just a rectangle. And you want to find an area of the rectangle. We already have the formula for that, which is length times width. My length is going to be 6 minus 2, which is 4. My width will be my height here, which is 8. So 4 times 8 is 32. Obviously, our graph will not be perfect all the time. We don't have formula for it. So if you want to find the area under the curve, if you don't have formula, we can apply limit definitions, which I'm going to do in this example. We should get the same answer, which is 32. So I have an integral from 2 to 6, 8 dx. This is my f of x, right? F of x equal to 8. And my integral is in the interval of 2 and to 6. I have to calculate my delta x. The formula is b minus a over n. My b is 6, my a is 2, my n, we just keep it n for now. Eventually we're going to take a limit as n go to infinity. So my delta x is 4 over n. Next step, I'm going to calculate my CI. The formula is a plus I delta x. Again, my a is 2, my I is variable, delta x I just calculated here is 4 over n. I rewrite a little bit over here. Next step, I'm going to plug it in the formula. This is the formula. So I'm going to have limit as n go to infinity. Norm of delta go to 0 is the same thing as n go to infinity, which means the width of the rectangle is approaching 0. Now sigma I from 1 to n, f of ci, this is my function, which is f of x. It's just constant. So I'm going to put the constant here. My delta x is right here, 4 over n. Next step I did is I multiply 8 and 4, I get 32 over n. I apply definition of sigma constant. Remember, if you have a sigma of some constant, it's just constant times the upper limit here, which is 32 times n. And my n here is the same n here. I reduce the n, limit of constant, it is constant, which is the same answer. It's a lot of work, but just to show you how to apply limit definition. So before the end of this section, I would like you to read definition of two special finite integral, which is these two. Basically, it said that if you take an integral from a to a, f of x dx, you're going to get 0. So if you have an integral from 2 to 2, or whatever that is, you're going to get 0. Basically, it's just one spot. You don't have area. If you take an integral from b to a, f of x, I forgot dx here, invisible dx. So you can flip from b to a to b, but you must put negative here. Okay, so I forgot to put dx. I corrected dx. All right. So you can swap the lower and upper bound, but make sure you put negative. That's allowed. The third one, if you have an integral from a to c f of x dx, you can break it down into two or more parts. For example, this one you can take an integral from a to b f of x dx plus b to c f of x dx. Make sure that the b here is between a and c. Alright, so we finished 4.3. I'll see you next time. Bye.